Hello everyone, welcome back to Bytes of CAC. So in this lecture, we'll learn about the RSA algorithm. So RSA algorithm basically is an asymmetric key algorithm where there are two keys used in the system for sending cryptographic messages. Say Virat is a person who's connected to a crypto network that uses RSA algorithm for encrypting messages. So Virat basically has two keys with him. One is the public key, which is shown in this silver, and this public key he shares with all his peers in a network, and there is a private key which he keeps to himself. Now, say Anushka likes to send a message to Virat. So what Anushka will do is Anushka will get hold of this public key, that is the key that is shown in silver, use this key to encrypt the message. So algorithmically, if I say basically encrypt is a function that takes as input the message and the public key, and it outputs something which is the encrypted message. Now this encrypted message is sent over the network to Virat. Now Virat will use his private key, which is confidential to him, and using that private key he will decode the message which Anushka has sent. So basically, decrypt is a function that takes in as input the encrypted message that Anushka had sent him and the private key, and it outputs the original message that Anushka had intended to send to him. Now let's before that, now RSA algorithm is based on integer factorization, where it is said that product of very large prime numbers are hard to factorize. Now let's see how RSA algorithm works. Now it works in three steps. So the first step is the modulus generation. So here what happens is we choose two very large prime numbers A and B, which is of 1024 bytes. Now side by side we'll walk through an example implementing this algorithm. So here let us consider our A is 3 and B is 11. Now these are prime numbers, but definitely not very large prime numbers. I've chosen a relatively small prime number just for ease of calculation. So next we need to calculate a number n, which is the product of A and B. So in our case, the n will be 3 into 11, that is equals to 33. Next is we need to generate the public key first. So basically we need to calculate another number z, which is equal to a minus 1 into b minus 1. So in our example, a minus 1 means 2 and b minus 1 means 10. So our z will be 20. Next, we will have to find a number e which is relatively prime to z. That is the greatest common divisor of e and z is going to be 1. That is, they don't have any common factor other than 1. Which means, now if we consider this 20 and consider all the numbers lesser than 20 which are relatively prime to this number 20, we get a list like this. So 3, 7, 9, 11, 13, 17 and 19. See, we don't have any common factor between any of them and 20 other than 1. So from here we choose the simplest one, that is 3. So this is going to be your public key, which is to be distributed among the peers. Now A and B will be kept secret. So this E will be shared, and also this N will be shared. This pair will E and N pair will be shared as the public key. Now we have to generate the private key. Now private key is generated using this formula: E into D equals to 1 mod Z. Now you get E from this step here, you get Z from this step again, and this D is your private key. So if you look into this example, we have E equals to 3 and we have Z equals to 20. So for this formula to be to introduce this formula, so E into D can be 21, 41, 61 and so on. So basically 20, into some integer, say x or y, plus 1 is going to be the is going to be e into d. Now we know that 21 is divisible by 3 and the result is 7. So in our case, the value of d we choose to be 7. Now in real practice, this d is chosen using extended Euclid algorithm, which takes in a, b and e and computes d. I'm not going to discuss about extended Euclid in this lecture. So now d is this private key that the receiver keeps as a secret to himself. Now let's see how is it applied to any message. Say you have a plain text message, you will have to divide that plain text message into k bits such that 2 to the power k is less than n. So this is a message of k bits, another message of k bits, and so on. Now let us consider that this message of k bit as, let us designate that as p, that is a plain text message. Now the encryption function works using this formula. Now this c is the encrypted message and this is the p that the sender needs to send. So p to the power e mod n gives c. Now you have this e, which is the private, which is a public key that the receiver shares, and n also is something that he shares. So using that you get this encrypted message, and now at the receiver's end the decryption function works as p is equals to c to the power d mod n. So this c is sent over to the receiver, and here d is the private key of the receiver and n is something that was calculated before. So therefore if you apply this formula you will get back this value p. So now let's take a real example where we will be applying all of these. So we are considering the same example, the same key value pairs that we had chosen. So we had E, which was the public key, as 3, we had the private key as 7, and your N was 33. And this was all generated using this formula. I hope you remember that. Now, so what we have is the sender receives a public key value pair as 3 and 33, and the receiver keeps a private key value pair 7 and 33 to himself. Now say the plain text message that sender is sending to the receiver is R, the plain alphabet R. Now if say the alphabets are codified in a way where A starts from 1 and Z is at 26, so that makes R equals to 16. Okay, sorry, 18, sorry. That makes R equals to 18. Now, as you know that C equals to P to the power E mod N. So here your value of P is 18 and this value of E is 3. So let's compute P to the power E first. So 18 to the power 3 is going to be 5832. Next we have to compute the modulus of n over this number. So that is equals to 5832 mod 33, which is equals to 24. Now this value 24 is sent to the receiver. Now at the receiver's end, as we have said, now this P is equals to C to the power D mod, this is a formula for this is how mod is depicted, mod n. So now 24 to the power 7, that is the value of D, is this big number. I just use the calculator for this. Okay, and now we have to take mod 33 over this number, and that is equivalent to 18. Now if the receiver, and of course receiver knows that how this coding scheme works in case of alphabets, so he can easily change that to R, which was the original message that the sender intended to send to the receiver. Now let's look at a sample question. So most of your questions are based on this: finding Z, finding E, finding D, and so on. So in this question, we have the value of A as 30, B as 31, D is given as 7, and we have to find the value of E. So let's get started. So first we have to find the value of Z. So here the value of Z is A minus 1 into B minus 1, that is 12 into 30, which is equals to 360. And now we know that E into D or D into E is equals to 1 mod N. So here your value of D is 7, value of E is unknown, and this is what you need to find out. So the potential candidate for this product will be 361, 721, and so on. Now 361 is not divisible by 7. So 721, if you divide it by 7, it gives you 103. So you can write that your value of E is 103. Now if you have a higher value, say you have, say whatever be it, 360 into N, and N was higher than 2, plus 1 equals to something, and that was also divisible by 7, and if you had outputted that value as your E, it would have been the same. So generally what we do is we look for the easiest one or the closest one. So that is 103 in our case. So that was all about RSA algorithm. So there is a website where I have put some questions regarding this RSA protocol. I would highly recommend you to go through those questions, try solving that for a better understanding. So that was all for today. So thank you for watching, and do share it with your friends if you have liked my video.